Okay, green 4. So what we have here is we got a vector field, we have a curve, and we want to compute a line integral. Right? Different options. You can try to, in fact, the curve's parameterized. You could just chapter 5 style compute it directly, but I don't recommend. I mean, it's usually the case that there's a more clever way around, especially when you're in a section on boundary theorems, where it seems reasonable. Again, you're going to want to try fundamental thermal line integrals. Sometimes that'll work, sometimes it doesn't. In this case, if I'm looking at this correctly, let's see here. I believe it's not going to work. Yeah, not going to work. And it's not immediately obvious why it's not going to work, but it just isn't. Okay. Yeah. So we're going to use Green's theorem here. Now, in order for Green's theorem to apply, you have to make sure that your curve is a closed curve, because it's got to be a boundary of some region. And is that the case here? Well, t goes from 0 to 2 pi. The curve is sines and cosines. In fact, this is exactly an ellipse like this of semi-x-axis. Let's call it the x radius is equal to 2 and the y radius is equal to 4. Does that make sense from the parameterization? Okay. So it really does go all the way around. This really is the boundary of a region. It's even oriented in the correct way. And so the line integral that I'm interested in is a line integral around a boundary of this region D. So I can compute it with a double integral over D itself of my Green operator of F. So we are going to have to compute that Green operator now. So, okay, well, it's just, algebra, dq dx minus dp dy. Conveniently, Q's got mostly y's in it, so dq dx is just -2. dp dy, well, again, though, all that x business goes away because we're taking a y partial, and it's just -3. And altogether, I have double integral over that disk of, let's see, 1. Oh, excuse me. Oh my gosh. Okay. That make sense, everybody? So conveniently, I would say that the constant factors out. I don't even need to factor it. It's just 1. So this is just the area of that region, and the area of an ellipse is something that we know how to calculate. In fact, there's a problem later on. Yeah, it looks like 639, exercise 9, has you confirm. And by the way, general rule, if you have an ellipse, right, where that radius is A and that radius is B, then the area is pi AB. And again, that's what you prove in 639 down here. Oh, well, okay, it's not written down in the statement of the prop, but I claim that that's what the answer is, pi AB. Yeah. So in this case, A is 2 and B is 4. So this is 8 pi. That make sense?